channel MS2 Physics, where physics gets charged. Today's video will discuss the electrical intensity to 6 charge particle systems, right? So in this I am taking 5 charges, all are identical, are placed at corners of a regular hexagon of side R. So my intention is to find the electric field intensity at empty corner. So at this empty corner we have the electric field to all the 5 charges. As this is a positive charge, like for our convenience it is the first, second, third, fourth and fifth charge particle. So due to this first charge particle, you took it away from the positively charged one, so you can write as E1 and at the distance of R. And due to the second charge particle, the line joining from point to that second charge particle is definitely of root 3R, the regular hexagon. So and it is a positively one, so that because of this is also away from that positively charged particle. And again, due to third charge particle, so the distance from point to that third charge particle is at the distance of 2R. So because of this, again this away from this only is a E3. And now the fourth charge particle is at the distance of again root 3R from this point. So due to this is away from here is a E4. And now due to fifth charge particle is at the distance of R only, because regular hexagon. So this direction is away from it, means of this fifth charge particle. So here it is of E5. Okay, so now at first I am taking the directions of electric field strength at this point due to individual charge particles. Now I am coming to simplify one after the other. At first I am taking a resultant of E1 and E5 at first. And I am coming to resultant of E1 and E5. Why? Because this first and fifth charge particle at equidistance and the angle between them is 120 degrees. So here we can write E1 is equals to E5. This is equals to that 1 by 4 pi epsilon is supposed to be K. So that here we can write K Q by R square. And theta between them is 120 degrees. Well, because when the adjacent sides in the regular hexagon is 120 degrees, so here between E1 and E5 we can take as 120 degrees. When two vectors of same magnitude, okay, and the angle between them is 120, so the resultant of 1 and 5 is 2, either E1 or E5. Cos 120 by 2 is a cos 60, cos 60 is a 1 by 2. So again you will get a E1 only, means E15 is equals to, we can write again K Q by R square, and its direction is angle bisector, so should be of 60 degrees. So it is a 60 degrees. See, from here to here it is a 60. So along this direction only we will have E15. We will have along this direction E15. Right now I am trying to simplify the resultant of 2 and 4. The resultant of E2, resultant of E2 and E4. Again, when coming to write the magnitudes of E2 and E4, because of these 2 points are equidistant from the point where we are going to find the electric field strength. So, and that distance is a root 3R, so which is equals to, we can write K Q by R square. R is what here? Root 3R. Root 3R whole square, which gives what? 3R square. Right? And angle between these two is definitely of 60 degrees. So when it is a 60 degrees, so when the two vectors of same magnitude and the resultant is a angle is a 60, the resultant of the two is 2, either E2 or E4. Cos 60 by 2 cos 30. Cos 30 is a root 3 by 2. So that we can write E24 as root 3 times of K Q by 3R square. And as the magnitudes of the two are same, then definitely the resultant should be of angle bisector, means it is an angle of 30 degrees. When it is an angle of 30 degrees, it should be again along E3 only is a E24. Means now, if you are observing this vector diagram, the resultant of 1, 5 and 2, 4 and E3 all are along the same direction only, so that the resultant electric field strength or net electric field strength at a point P can be written as E resultant is equals to, we can write as E3 plus E15 plus E24. I am not adding the resultant electric field of all, I am adding vectorially because of all are in same direction. Simply I am taking E3 plus E5, E15 plus E24, right? So now by using this, here we can write ER is equals to E3. This third particle from the point is at the distance of 2r. So can I write a K Q by 2r whole square is gives 4r square plus E15 we got here is a K Q by r square plus E24 this one we got here, can I write a K Q by root 3 r square, well, because root 3 by 3 is gives root 3 here. Therefore E resultant at an empty corner is K Q by r square taking common, so that here we can write 1 by 4 plus 1 plus 1 by root 3. Depends on the options. 1 plus 1 by 4 can be written as a 5 by 4. So K is here 1 by 4 pi epsilon Q by r square of 5 by 4 plus 1 by root 3 is the resultant electric field strength at an empty corner of a regular hexagon, right? So now if you want to find, all the charges are identical and are supposed to be positive only, but now if you want to find the electric fields at the center of the regular hexagon, means I am coming to the diagram at first. This is a regular hexagon of side R. Okay, 6 charge particles of magnitudes Q, Q, Q and Q and Q. So my intention is to find the resultant electric field strength at a center. Resultant electric field strength at a center. Okay, so now again for convenience, giving the numbering to these charges 1, 2, 3, 4, 5 as well as 6. So at the center O, due to first charge away from it, so it should be of E1. Okay, and due to second charge particle, the direction is along this is a E2, and due to third charge particle it is a positive one, so along this is a E3, and E4 is along this, and E5 is a positive one along this direction, and E6 is away from it is again is this. The important thing is, from this center, all the charge particles are equidistant and the distance is of r, so that when I am taking the resultant of 1 and 4 is a E1 minus E4, which is a 0. Which is 0 or not? Why? Because the magnitudes are same. Similarly, E25 is a E2 minus E5. Then again these magnitudes are equal, so its resultant is 0. And coming to the E36, these two magnitudes are also be of same, so this resultant is 0. Therefore, the net electric field strength at a center of a regular polygon, either you may place all are positively charged particle or you may take negatively charged particle. The difference is, when you are taking negatively charged particle, it should be of E1, it is the E4. It should be of E5 and it is the E2. And this is of E6 and it is the E3, is only the difference, but the resultant is same here. The resultant is same, is a 0, right? So my point is, you are trying to solve the same problem by taking alternately positive, negative, positive, negative, positive, negative, and find the net electric field strength here. Okay, stop the video and try to solve it. Now here alternately positive, negative, positive, negative, positive, negative are placed at 6 corners of a regular hexagon, and I am going to find the resultant electric fields at a center. Okay, so when this is a first charge particle, so due to this the electric field is towards the fourth particle, and due to this fourth charge particle, as it is a negatively one, so towards the fourth only, right? And now coming to the second charge particle, as it is a negatively one, so that it is a towards the negative charge particle is a E2, and coming to the fifth one, as is a positively charged particle, so that it is away from positive, so towards the E2 only E5 will be present, And now coming to the E3, as it's a positively charged one, so along this is the E3, and when it's a negatively one, sixth one, so towards the negatively charged particle, the sixth particle, sixth electric field strength will be towards negative one. These are the electric field directions due to individual charged particles. And one more thing here, all the six charged particles are at equidistance from the center of this regular hexagon, and that distance you may take as r only, so that here can I write E1 is equals to E2, that is equals to E3, and E4 and E5 and E6, that is equals to KQ by R square. K is nothing but again 1 by 4 by epsilon. Okay, so at first I am taking the resultant of 1, 4. This 1 and 4 are in same direction, so that can I write K into 2Q by R square. And next I am taking the resultant of 2 and 5. So this 2 and 5 are also in the same direction. So can I write K into 2Q by R square. R is the distance of that point to the respective charges. And again here E36 is again same, is of K into 2Q by R square, but is in leftward direction. And direction not mentioning here, and directly I am giving the directions in the vector diagram only, right? So now my point is E14 and E25, E14 and E25, they are equal in magnitude, and that magnitude is K into 2Q by R square, 2Q by R square, so that angle between them is this. This is definitely of 120 degrees. Is a 120 degrees when the two vectors are equal in magnitude. Okay, and at an angle theta, the resultant of 1, 2, 4, 5, the resultant of 1, 2, 4, 5 is equals to 2E14 cos theta by 2 is a cos 60. Cos 60 is nothing but 1 by 2. So which is again, which gives us E14, means the resultant of these 1, 2, 4, 5 is towards rightward, and that magnitude is 1, 2, 4, 5 is the magnitude of K 2Q by R square. Is a towards right. What is in the right? It is a towards rightward. And this E36K into 2Q by R square towards left. So the resultant electric field strength at the center of this regular polygon is the difference of the two is nothing but E1245 minus E36. If you are observing here, the magnitude of E36 is a K2Q by R square, as well as the E at a 1245 is also be K2Q by R square, which means they are equal in magnitude but opposite in direction. Therefore, the resultant electric field strength at a center is also be 0. Means if you are taking all are positive charges, all are negative charges, then the electric field strength is 0 at a center. And even if you are taking alternately positive negative charges, then also we got the resultant electric field strength at a center is of the regular polygon A hexagon is 0. So now in a higher level, for the same given arrangement, they may be asking the expression for electric field strength at a distance r from the center of the polygon, the center of the hexagon, but normal to its plane. Which means now as these all are the distance, now the point is here. The point is here. Understood? When the point is here, it is normal to the plane. So we have the electric field strength to respective all the 6 charges, and should take the direction. Then coming to simplification. So this will be explained after the concept of dipole. I will take this problem definitely in the further videos. Got my question here? It is the same arrangement, but now the point is not at a center, at the distance of r from the center and normal to its plane. Normal to its plane here. This is what I will discuss after the concept of dipole. Thank you students. Thank you for watching. If you are like my videos, do like, share, comment and subscribe our channel to get more videos.